we want to see how we can write equations of a polynomial if we know the zeros. Okay? So we want to take a look at what happens between our x-intercept and our factors. So if we have this equation right here of x minus 3 times x plus 4 equaling 0, notice our two x-intercepts are 3 and negative 4. So notice from here to here, we change the sign. From here to here, we change the sign. That's really because we're doing x minus 3 equals 0. So then we add 3, so x is 3. And x plus 4 equals 0. We want to undo adding 4, so we subtract 4, so we get negative 4. Right? So we can use this same kind of process, but just backwards. So we have usually been given the factors and we're finding the x-intercepts, but now we want the x-intercepts and we want to write it in factored form. So I want to go backwards. So if I know my x-intercepts, I can find an equation. So I'll find an equation for a polynomial in factored form. Okay, this is important. It means it's less work also, with the following zeros. So we have the 0 of 2, 5, and 3, and the 3 has a multiplicity of 2. So we've got x equals 2, x equals 5, x equals 3, and that has a multiplicity of 2. Okay, so I'm going to undo moving it to this side. I'm going to move it back over with the x. So here I would have to subtract 2, or you can think I need to change the sign. I need to move this one back over to the left, so I'm going to undo adding 5, so I'm going to subtract 5, or remember, you change the sign. Here, I'm going to move this one to the other side, so we're going to subtract 3. But the multiplicity 2, remember the multiplicity is the power that it comes from, so this has a power of 2. Right? So then this would be my equation in factored form. Now this is not the only equation, because I could get these zeros with another equation where I have something like this, where I have 2 times x minus 2 times x minus 5 times x minus 3 squared, right? Where all I've done is change the number out in front. Okay? I could even add more zeros. So I could have another one where I've got f of x equals, I could do negative 4x cubed times x minus 2 times x minus 5 times x minus 3 times 2x plus 1, right? Because it has these zeros. It didn't say only these zeros, so I could have more zeros than that. Okay? So that there's a whole bunch of answers that you could have for this one. If we look at the next example, this one is more specific because it says find a 4th degree polynomial in factored form that has these roots. So this one didn't tell us what our degree was. This one specifies the degree, so we only have 4 zeros that we can have. So we have 0, negative 2, and 3 plus 2 root 5. Well, if I have 3 plus 2 root 5, that means I also have 3 minus 2 root 5 because our conjugate theorem. So I know I have this additional 0 in addition to this one. Okay? So I set x equal to 0, x equal to negative 2, x equal to 3 plus 2 root 5, and x equal to 3 minus 2 root 5, because we know there's conjugate pairs that these come in. So here, if I move that to the other side, it's really just going to be x minus 0, which in a minute will drop. If I change the sign here, this will be x plus 2. If I change the sign on this one, I'm really subtracting the 3 and subtracting the 2 root 5. So then I'll have x minus 3 minus 2 root 5. If we look at this one, I have to subtract 3 and add the 2 root 5. So I'll have x minus 3 plus 2 root 5. Right? Notice again, these signs are the same, but these ones are opposite because they come in conjugate pairs. Only the middle one changes. Okay? So if we look at our degree, I would have x times x times x times x, which is x to the 4th. So I can't add any extra x-intercepts here because we're only allowed a 4th degree polynomial. Now I can write this a little bit nicer so that we've got x plus 2, x minus 3 minus 2 root 5, and x minus 3 plus 2 root 5. Okay? Again, the question asks for it in factored form, so I don't need to do anything beyond this. There's also a plethora of answers that you could have here because I can multiply any number out in front, just a scalar number with no other variable, and get a different polynomial, but where I get those same x-intercepts and it's still a 4th degree polynomial. Okay. Now, this one is a little bit tedious and not fun, but we are going to deal with it anyways. So find a third degree polynomial, so our degree is specified, with rational coefficients that has the roots 6 and 3 minus I. Okay, notice this one doesn't say factored form, so we've got our rational coefficients, which means I have to multiply it out, which is a bummer, because that's not our favorite thing to do. Okay. So if we know the roots are 6 and 3 minus I, well, I also know that I have 3 plus I. So I have x equals 6, x equals 3 minus I, and x equals 3 plus I. Okay. So I want to move it so that I have everything on the other side. So I'm going to move the 6 to the other side. I'm going to move the 3 and the I to the other side. So I get x minus 6, x minus 3 plus I, and x minus 3 minus I. Okay. But because we want our rational coefficients, I need to multiply this out, and it doesn't say that it has to be, or doesn't specify factored form, so I have to multiply this out. Now, I could multiply these two, or these two, or these two. It doesn't really matter. It will be faster and less tedious if you choose these two, the conjugate pairs, to multiply together. Also, I would highly recommend that you set up a box for this because it makes keeping track of the numbers easier. So we have x minus 3 plus I and x minus 3 minus I. So in our first row, we've got x squared minus 3x plus ix. In our second row, we've got negative 3x plus 9 minus 3i. Right? All I've done is x times x is x squared. X times negative 3 is negative 3x. X times I is ix or xi. Either one is fine. Negative 3 times x is negative 3x. Negative 3 times negative 3 is 9. Negative 3 times I is negative 3i. And then in our third row, we're going to do x times negative I is negative xi, or ix. Both are the same. Negative I times negative 3, which is positive 3i. And then we have negative I times I, which is negative I squared. Okay. So now I'm going to look for like terms. So notice these two are like terms. We also have these ones are like terms. And we have these ones are like terms. So here, this goes to negative 6. Okay, so let's start with the x squared, then the minus 6x. So x squared, and then minus 6x. And then here, these are like terms. Even though I have the xi and ix, they're still like terms because they have the same variable with the same exponent. This is negative 1, this is positive 1, so this goes to 0. If I look at these like terms, I have positive 3 and negative 3, which goes to 0. Then I've got the negative I squared. Well, hopefully you remember that I squared is really a negative 1. So if I do that over here, then these two end up being like terms as well. So then the 9 and the 1 are like terms. So I do 9 plus the 1, which gives me plus 10. Okay. So that's what this part multiplies to. This is why you want to multiply the conjugates together first, because they cancel things out. So then I still have this times x minus 6. So now I'm going to multiply all of these together. So I'm going to do x minus 6 times x squared minus 6x plus 10. Yes, plus 10. So again, I'm going to do my first row. So we've got x cubed negative 6x squared plus 10x and minus 6x squared plus 36x minus 60. Okay. So these two are like terms, and these two are like terms. So then our final polynomial, or one of our options for our polynomial, I don't need parentheses, is x cubed. Negative 6 and negative 6 is negative 12. X squared, what is that number? 36? Yes, 36 and 10 is 46. And then minus 60. So that would be our equation of our polynomial. Again, It doesn't specify either our end behavior or what our leading coefficient term is, so I could multiply this by any scalar number, so just like 2 or 3 or 4 or -6 or -7, okay, and get another polynomial that has everything that I specify. You couldn't multiply by a half because not a half would work because the half is still rational. I couldn't multiply by something like pi, even though it's a number, because it specified that it needed rational coefficients. Yes, this is annoying to do, but yes, you need to know how to multiply it out to find your equation of your polynomial.